this is the appendix. So you can take note, write down whatsoever. However, the formula will be given inside your exam as well. Okay, it shows here the basic formula of how you want to find your TJ. Here we have TJ for the device that attached with no heatsink. No heatsink attached. So the PD, dissipated power, times R thermal from junction to ambient plus ambient temperature. If you have heatsink, so you shall have three kind of resistance, thermal resistance between your junction to your ambient. We have here three resistors. Junction case to heatsink, heatsink to ambient. So this is the two generic formula for the heatsink consideration. When the junction temperature due to conduction loss, without heatsink, with heatsink. Okay, then when we have issues whereby we are switching the converters at higher frequency, so we have to consider the frequency amount or frequency values of the converter, because we have to add up not only your losses due to conduction loss, but due to switching loss. And so the contributing losses is during switch off and also during switch on. So how much of power absorbed by your switch, or you have your switch applicator, is by multiply your switching frequency times energy that it emits during off operation. So how much of operation depends on your drain current, and I drain current times your VDD maximum times your T on divided by 2. So this is the amount of your area below your switching on and off triangular waveform. Okay. Sometimes we can simulate inside our lab. Sometimes it does not provide this parameter, so we have to calculate and also called project during by using calculation. Sometimes we cannot simulate. So it depends on the recent eSIM software that you have download. You can simulate or not. Kalau you boleh tengok dia punya pattern macam mana, so you can simulate lah. Not you have to project using calculation. Okay, during switch off, just now during switch off, during switch on, how much the losses depend on the on energy it absorb. Also the same ID at on times your maximum holding current, maximum blocking current, VDD, V drain times T on divided by 2. So this one, I think the current is in RMS current. ID RMS. VD is in peak. So we'll check the third one. So because here we have here how much RMS current here. Then we have calculate. Based on peak current, we get average current, then we get RMS current. So the RMS will be used afterwards to find the thermal consideration that we have to consider for our switch. Okay, that's the only formula that needed and been shared. So now we shall discuss in terms of generic consideration on how you want to assign or how you want to size your switch. Okay, when you have a circuit or you have a converter, you shall need some sort of selection of switch to be attached or to be used inside your converters. Okay, if you open this element 14, for example, this is the most what's it called nearest supplier stock available with complete reference. If you type element 14, So you come out this page, come out with this front page actually, and front page. So you can key in here, MOSFET or whatsoever. Say you in MOSFET. So come out with this kind of selection. We have here all the discrete semiconductors which are available. So we have discussed in terms of what are our selection of features, which is transistor, thyristor, semi-control device, transistor, fully controlled device. We have here IGBT instead of MOSFET. We have IGBT as well. We have diode. This is your modules combination between the power MOSFET. So we have other than that, which is so it's stated down into specific selection. Our selection of MOSFET, single MOSFET, dual MOSFET. So we look at single MOSFET first. Okay, about 12,000 products found. Okay, what are the specific parameters that we should put in mind to select around or among these 12K of products to be used in our device or our computer we use as our device. So the main part or main parameters is continuous drain current. See here, how much is our continuous ID that we need for our system. So we have discussed in terms of our SOA, safe operation area. So let's say you are looking for, you calculate your design unit, some sort like a few amperes. Let's say you need around how much ampere? Okay, you need around maybe 20 amp and 20 ampere to be accomplished to complete your, or 20 amp to complete your design or to finish your design. So you put here an exaggerated values of 20 amperes above. So let's say we put here 29 ampere for safe range. So we have here 43 products. Then what are our required voltage that should be the device can withstand? So maybe it should withstand around 400 volt. So we took a next step of voltage range, which is 600 volt. And so this is to play safe. And to play safe, we put one range higher to evaluate our device. Okay. Because this is the time whereby we just look at the dashboard and say this part can extend up to 29. We need only 20, let's say. We need the part to withstand up to 400 volt. And if you rectify to 140, become 400 volt DC. So 400 volt. So we take one step higher, which is 600 volt. So we come out with this 22 section of product. So the next step is to evaluate. Maybe we take a few parts to compare in terms of their performance and to be our candidate of our switch. So you have here. And usually we shall compare between two different manufacturers. And maybe we can compare between one manufacturer as well. Okay, because we have here. Say this one came from STM as well, STM Microelectronic. This one also STM Microelectronic, but at different price. See here, different price. So the most popular is we select based on price, then we take a look at their performance. Maybe the cheaper price, cheaper heatsink, some part higher price, cheaper heatsink, so it doesn't, we don't know. So we have to evaluate. So let's say we take any two parts as consideration. Actual, you have maybe to take into consideration up to 5 or 6 parts. You have to skip. Then choose the two best and propose one. And so let's say we take a look at different manufacturer to see in clear how the comparison should be done. So we take these two. Let's say this one from Semi, this one from Vishay. So both are the same parameter, which can extend up to 29 ampere, 300 volt, 300 volt, but different manufacturer. Okay, so we put it side by side to compare. So compare the selected two. So we have here, this one only 80 ringgit, this one it costs up to 28 ringgit. So we want to see this one, how much the performance compared to this one, how much in terms of their performance. How much means that, how much does it cost to cater certain values of power rating, current values, voltage holding rating, when include with heatsink or without heatsink, how much the cost. Okay, we take a look at their data sheet, technical info. This one from Vishay, and another one from wait, I have shared the screen or not? Nobody tell me that I just miss this process. Semua bukan diam, no? Patut I share the screen, bukan share slide tu. Semua diam. Tu betul lah. I just talk alone just now. Okay guys. Oh, bagus lah. Saya dah discuss sampai sini ha. Rupanya saya tak share screen. Never mind, I just repeat it again. Okay. When you have what so-called a design, okay, you go into element 14. Luckily, I record this one, so you can repeat later. You go to element 14, you can type element 14 in your search here box. So it comes here, and when you type, let's say MOSFET and or discrete device, so we suggest you all what device we have as option. Okay, we have FETs, feed effect transistor, MOSFET, IGBT, or whatsoever. We have here diodes, we have the IGBT transistor, resistor. So it depends on the types of power switch that you prefer. Is it a semi-control or a non-controllable or fully controllable switch? And so it's specific down. Are you looking for single MOSFET or dual MOSFET or whatsoever? Okay, let's say you click this single MOSFET. So we suggest you all with 12K of products. And we have here 12,254 of selection products which available in the market from this producer lah. This so-called this what supplier. They're supplier. We just supply from all over the world across many kind of producer lah. Okay, let's say the first parameter that you have to choose is in terms of their drain current. How much the drain current that you need to use for. So let's say our product need to conduct 20 ampere. So you select the next level of values, which is 29 amp. As I told you before, if you look at your front page, it will show you the dashboard. So for safe play, we take a little bit higher of voltage and current range. So the first thing, you select your current range. You need 20 ampere, but you select the next higher, which is 29 ampere. We have other range of current as well. As you can see here, the drain current, this one. And have here. We need 20, but why we take 29? Because we have about how many selection? 43 products instead of the other selection. Also we have here 28 ampere, 55 selection, but for 27 we have only one, so this one is not set because we have only one selection. So we take the next which has many selections, so we can compare in terms of the out of a multiple of selection which one is suitable for our product. Next is to select in terms of our voltage range. Let's say we want to run under 24 VAC. If we rectify, it becomes 400 volt DC. So we take the next values of 600 volt. So let's say we need only 400 volt. Yeah, this one. Range source voltage. We need only 400 volt. But it has here, so it's only 100, 150, 600. So we take the next higher voltage, which is 600 volt. So it shows here, and you click 600 volt, narrow down into 22 products. Just now 40 something, so narrow down into 22 products. So based on these 22 products, we shall select a few more to specific down to which one should be appropriate for our design. And usually we shall cross-check or compare between two different manufacturers. It might be from the same manufacturer, but it does not bring any significant attributes or comparison. So maybe from same manufacturer, you can compare based on the price and based on the total energy, cost per energy, cost per product, cost per system. But for the time being, we just compare between two different manufacturers, which is, so just now we compare between Vishay and onsemi. So this one, you click Vishay and onsemi. We have here, same, 600 volt, 600 volt, 29 ampere, 29 ampere, but different manufacturer, onsemi and Vishay. So we click these 2 points. So we click at compare. So it come out with this compare product page. So it shows here in terms of their overall layout, package, body package, we have the black plastic encapsulate shape with a metal tag with a hole. So it means that this part need to be attached to heatsink and need heatsink to properly operate up to their maximum capability. And we have here what's so called channel type, N channel. This one also N channel. And the big difference is their price. Here, price. If this one can operate with a cheaper or less spec of heatsink, so this is perfect choice. But this one, if this one, even though it's high price, but the heatsink is cheapest compared to this one, so overall cost part per heatsink, with heatsink, part with heatsink for the same performance, so we shall choose that one. But other than that, we have other parameters to be considered as well. But for this moment, so that's the two critical decision to make. So other than that, just for your information, so we have here gate source threshold voltage. So this one also usually contribute to losses. This one 5 volt. This one only 3.5 volt. See or not? And gate threshold voltage. This one in terms of how you want to provide control or how you want to switch on and off this device, you have to provide the gating control circuit. So the one also contribute into cost, but it beyond our consideration for this moment. What else? This is in terms of their product version. Gen berapa type apa. Okay. Yes. Okay, then we go to the specific parameter of the datasheet. We click here, technical datasheet, compare the technical datasheet of our two products here. So it comes into one is from Fairchild just now, Vishay dengan on semi. Jadi Fairchild ni. So Vishay and yeah. Fairchild is now part of on semi. So dia dah merge kan. So sama lah. Okay. Satu is on semi. Satu is Fairchild. So you can see here. Look at their thermal consideration or thermal value. Thermal. So thermal resistant rating. For on semi, thermal characteristic. We have to here. So R thermal JC 0.48, R thermal JA 40. Just now, R thermal JC 3.6, R thermal JA 65. You see the difference? You see the price? Vishay is cheaper, on semi is higher. So Vishay cheaper, on semi is higher. But the thermal JC is 0.45. This one is 3.6. Voila. So now we can see the difference in terms of their values. Very big difference. So we have to consider up to the heatsink components or requirement for this part. We consider which one is better selection for our system. So far, we have any issues or any question? Ada soalan setakat ni? So we start to calculate now. Can bring out your paper and pen to start work up with me. Any question so far? Semua okay kah? Faham kah? Macam mana nak select sampai this step? This is applicable for your FYP as well. Let's say you want to consider your power switch, so this is the step. Anybody? Semua okay ya? Ahmed Sulaiman, are you okay? Zuhra, okay.
Yeah, okay, sir.
Bagus, good. Okay, I consider as all okay. Okay, we continue. Then, so the first thing is that we have to consider how much actually the system or the switch can operate without heatsink. That one have to be considered first. Okay, let's say we have here, even though stated of here, Vishay can extend up to high drain of 29 ampere. And when the operating temperature up to 100 degrees C, you have to derate it or reduce down to 19. Meanwhile, your on semi, we take a look at on semi, how much the drain current? 29 ampere. If you maintain case at 25, you cooling down to 25. So this is impossible. Go down, or it's not feasible, not economic. But if you set to operate at 100 degrees C, so you have to derate it or reduce the capability down to 18 ampere. Okay. Where is the pen? Can you see my screen? Seperti tak keluar. Wait, we take 5 first. I try to figure out how to draw this one. Okay. So far, any questions so far? Okay, can you see my screen? I'm drawing now. Can you see? Yes or no?
Yes, sir.
Can, huh? Okay. Okay, without heatsink. So without heatsink, we shall consider our device. So let's say we take one by one. So this is the what so called the issues or the, so we take on semi for on semi and for on semi device. So without heatsink. Without heatsink. So without heatsink, you draw your thermal equivalent circuit, draw nicely, and put a label thermal GA, TJ, TA. So this is your PD. So without heatsink, the equation with TJ equal to PD R thermal JA plus TA. Okay, usually your parameters to be accompanied with your design will be your how much is your ambient temperature. This one will be given. Ambient temperature. What else? Let's say your required current. Just now we said you need 20 ampere. V max 400 volts. This is the parameter that will be given. And then this is the parts or the components that you have to calculate or justify upfront. So TJ, let's say we take at 20% below maximum. Okay, 20% below maximum. So you take a look at your data sheet. What is your maximum TJ of your parts? Let's say we're considering on semi as our part. Okay, we have here TJ storage. This is our soldering temperature. So for junction and storage, this one, it can operate up to 150 degrees C. So 20% below 150. So is so TJ is equal to 150 minus 20% of 150. So how much? 150 minus 30 degrees. So you set your TJ at 120 degrees C. Or else you can calculate directly. TJ is equal to 0.8 times 150. Also you get 120 degrees C. Doesn't matter. So it's an open kind of selection or open kind of calculation way of step. Okay, next. You have to calculate your PD. So just publish step by step. Just now is your TJ, then your PD, then this one all you get from the provided information. So your PD is equal to I square RDS during on at 100 degrees 20 degrees C. RDS on at the temperature of your junction. So your IRMS already been given here, 20 ampere. But how much is your RDS on? RDS on 120 is equal to RDS on times. So you take a look at your data sheet. How much is your RDS on? RDS on is 102 milliohm. That one is RDS on at 25 degrees C. What happened at 120 degrees C? RDS on at 120 degrees C. Junction temperature, normalized. This one breakdown voltage. Junction temperature, RDS on normalized. See, RDS on versus temperature. This one breakdown voltage variation versus temperature. This also need to be considered, but our focus is on this one first. Junction temperature at 25 degrees C is here. See here, normalized factor is 1. But when we operate at higher, 100 degrees C, 150, 125. So 125 is around here. So 120 is around, let's say over here. So 2.0. See, 2.0. Anybody which cannot see or still blur, please highlight. Please normalize factor. Normalize factor. So 105 milli times 2.0. 105 milli. So 102 milli, sorry. 102 milli times 2.0. 102 milli times 2.0. So how much is that? 210 milliohm. So this is your 204. 204. Later masih tak. 204 milliohm. This is your RDS on at 120 degrees C. So your PD will be I square, which is 20 square times 204 milli, which is 81.6 watt. So this is your dissipated power when you operate your junction at 120 degrees C with 20 ampere of RMS current. So this is your PD. So what we want to see now is how much actually our junction to rise at this operating current. And our target is 120 degrees C. But what happened here? If we run full current, 20 ampere, without heatsink, and with this our thermal JA. So PD is 81.6. Our thermal JA for this device, our thermal JA is 40 degrees C per watt. Our thermal JA 40 degrees C per watt. 40 degrees C per watt. Ambient temperature is 40 degrees C. So calculate your TJ if you run without heatsink for this part. Apa jadi? Tiga, dua, enam, 4 tambah 40. So apa jadi ni? Apa jadi? Apa dah jadi? So you see the value 3304 degree C. Nampak tak? Apa yang nampak? Sekarang soalannya apa yang nampak? Node Farah, apa yang nampak? 2 node sini. Oh, 3 node, 4 node. Node Farah, node Rahifa dengan node Izati. What you can see here. Apa conclusion ataupun observation you can see from here, or you can observe from here. This is calculation. Let's say you want to apply for 20 ampere around 200 volt something, or 400 volt, 400 volt. So we choose next level of switch which can conduct at their dashboard. It says it can conduct up to 29 ampere. So we just use 20 ampere. Right? So it says that it can conduct or it can withstand up to 600 volt. We just use for 400 volt. So it should be no problem. But when we calculate, so we can see, oh, this is the expected junction temperature if we conduct this 20 ampere to this product without heatsink. So we see that calculated values of 3,000, how much? 104 watts kan? Nampak tak? So apa yang nampak? Dia akan nampak dia punya kesesuaian ataupun dia punya temperature will be exceed too much. So tak sesuai lah. You can buy and test and see your device burn. So that's one way lah. Another step is you can calculate first, project. If you put 20 ampere direct to your switch, so how much your expected junction temperature will be. So this is the expected junction temperature of the device without heatsink. Nampak tak? Untuk this part. So means that you have to put heatsink. Conclusion is that you have to put heatsink to cool it down into your expected junction temperature unit. Nampak tak? So sekarang kita kena kira how much the heatsink size. Or else if you say you don't have heatsink, so you can do the next step, which is you have to direct your current down to which value which is suitable such that your junction temperature will only rise up to 120 degrees C. So how will that be done? So let's say we want to check. We want to check how much actually our device can withstand the current in terms of the current if we want to use this device without heatsink. And so without heatsink, if you conduct 20 ampere and we conduct 20 ampere being conducted, so this is the scenario. You will rise your temperature up to 3304 degrees C. So next, we want to check if without heatsink, how much the maximum current here, how much actually can be used or can be conducted by the device. So without heatsink, if 20 ampere, so this is the temperature. But without heatsink, how much the maximum current? So we shall separate down. Semua boleh follow ke ni? Ke masih blur? Semua masih okey kah? Masih insert. Okay. Harap-harap masih alive. Okay, how much maximum current without heatsink? So still without heatsink, maximum ampere sama dengan berapa? So same formula you have to write, which is Tj equal to PD R thermal, because we have not yet used any heatsink, R thermal Ja plus TA. Same scenario just now. Ambient is 40 degrees C. This one is decided by your designer, your boss. You said you want to set your ambient at 40, so you just put 40. So without heatsink, and so we have set our Tj at 120 degrees C. Just now we just set our I load 20 ampere. Now we set Tj. So how much is our I load now? How much is our I load? So I load dapat berapa? At this moment. So I load berapa? Okay, Tj 120 degrees C. PD, this is the amount of dissipating power that we have to consider to maintain our junction. So thermal Ja just now is thermal Ja 40. 40. T ambient also 40. So 120 minus 40 is our PD times 40. So PD akan dapat berapa? That 20 minus 40 divide by 40, so dapat 2. 2 watt is our maximum. So PD of 2 watt is the maximum dissipating power to maintain Tj at 120 degrees C. So with this PD of 2 watt, so how much is our I? Okay, PD is equal to I RMS RDS on at 120 degrees C. So RMS RDS on Q adalah just now same 102 milli times 2.0 102 milli times 2.0. So kita dapat you punya I square RMS is equal to 2 minus 204 milli. So you punya I is equal to how much? .131 ampere. Clear? Is it correct or not? Anybody? Anybody? Dua no tadi tak menjawab pun. Ada sini kah? No. E1 ni nak. Betul tak? Pilih tu. Hello. Is it correct or not? Ayan Adrian.
Yes, sir.
Betul tak bila tu? Is it correct?
Tengah try.
Oh, I ask you all to do together with me. So, Jivinesh, understand
Yes, sir.
value is correct or not?
Yeah, correct, sir.
Bagus. Okay. Okay, you see? Now, if you want to stick with our requirement of when we set our ambient temperature at 40 degrees C, we want to maintain our junction temperature at 120 degrees C. So, the same formula here, same formula is this. Formula sama. This is the formula that we use. This is the formula that we use. The same. But come out with the conclusion that we want to stick our junction temperature 20 degrees C without heating. So this is the maximum current that can be applied. And maximum current can be applied. Yang first, just now, if you want to conduct 100% of the current, which is 20 ampere, so this is what happened. This is what will happen to our junction. We cannot maintain at 120 degrees C no more. It will rise up to 3004 degrees C. And for sure, before it rises to this value, it will damage and it will break or burn your switch already. So this is the consideration of the thermal before we pick up or place our device into the system or the circuit. This is very important. You want to proceed or produce your FYP or your project letter. So this is the thing that you have to consider. With full current, this will happen. With without heating, if you want to stick or maintain junction temperature at certain value, so you have to maintain or reduce your current down to this amount. Okay. Okay, then we shall consider how much actually if you want to maintain this full current. This full current to be maintained, you want to use up to this full current, how much you want to consider heat sink? to be attached to this part. So this one is without heatsink. So we consider the same part number, the same manufacturer with heatsink. So now we consider with heatsink. On semi with heatsink. Don't just listen, please do together. Okay, now with heatsink. Still on semi. Now with heatsink. So when with heatsink, we have one source, we have three resistant elements. One is our ultimate JC, ultimate CS, ultimate SA. The heat generated at junction will be dispersed down to ambient. We go through case, heatsink, and ambient. Okay, this is your MD. Voilà. So the equation will be Tj equal to PD R thermal JA plus R thermal JC R thermal JC R thermal CS R thermal SA plus. So usually GA will be given, and then R thermal CS either you are being provided or given data sheet. Let's say we provide your R thermal CS of 0.5 C per watt. So this is the heatsink value that you have to find. How much heatsink size? Okay. TJ you have calculated just now, 120 degrees C. So 120 SPD ultimate JC. You take a look at your data sheet. For ultimate JC of your on semi, just now is ultimate JA. Now we use heatsink. You shall use ultimate from junction to case, which is 0.45. 0.45. 0.45. Ultimate CS is 0.5. Ultimate SA is the heatsink value that we have to find. So we have two unknown here. One is our ultimate SA, one is our PD. So settle for PD first. Find out what is our PD value. But PD is equal to I square RDS on 120 degrees C. So your current is 20 ampere. So 20 square times RDS on. 102 102 milli. Times 2.0. So you will get how much your PD. That's 2.6 watt. Answer 2.6 watt. Then 103 degrees C. You take it back your formula just now. So to 81.6, 0.45 minus 0.5 plus thermal SA plus 40. So you calculate through, you will get your thermal SA of how much? And this whole step, this is just what's it called, shortcut. You punya formula, then go direct to your answer. In between, you should have your calculation step which has mark as well. Nampak tak? Maybe this one is 1 mark. If your calculation 1 mark, answer also 1 mark. So please do it properly. Source of insufficient space, so that's why I just jump daripada formula down to answer. Can anybody confirm my value here? 0.03 degrees C for what? The required heatsink value. Anybody? Ni dia juga ni. Tak share kat screen tu. Semua diam ni. Line down, sorry guys. Semua okey ke? Hello. Hello, semua okey ke? Anybody can confirm my calculation? Okay, doctor. Please, thank you.
Betul, sir.
Apa tu? Tak semangat je. Okay. Sorry, tadi miss line down. Okay, you can see the step. Now, okay, with heat sink. So now we consider with heat sink. With heat sink. So three elements involved. So this is the formula. So we put the expected junction temperature that we want to set. So this is the value of our ambient temperature. The value from the data sheet. Junction to case to heat sink. And the value of P dissipating power at this moment. So PD calculated based on the maximum current that we conduct inside our circuit, 20 ampere. RDS on is our consistent at setting of 120 degrees C junction temperature. So this is the PD that will be dispersed at the circuit device, the device itself. So with this PD, we can see that, and we insert back into our calculation. And please calculate and also mention the step in between your formula here. Before you reach to your answer, there are a step. So please furnish the step as well, because the step also has mark. Maybe this one is 1 mark, step 1 mark, so answer 1 mark. So if you don't put your formula, don't put your step, you have as all the answer. So if your answer is wrong, so all will be wrong. So we calculate, we found that with the size of heat sink that we need to find or attach to our system, such that it can conduct 20 ampere is 0.03 degrees C per watt. Voilà, 0.03 degrees C per watt. So it's such a huge and very effective aspect of heat sink. It doesn't matter. So that is the final, not final, almost the final step to compare between this part and versus another part, which is we just now consider two parts. One is our on semi. Another one is our V shape. V shape. So same process applied to V shape. Just now we consider on semi. Now we consider the V shape up to the heat sink size. And so please repeat on the V shape. Semua okay kah? So the same process we apply. By right, the comparison should take place on multiple parts, across multiple part number or manufacturer. But this just now, for this case, we just consider between two manufacturer. So you just see, hilang pen tadi. Okay, now V shape. Okay, V shape. V shape. Can you get this? S-H-A-Y. Okay, V shape. V shape without fixing. Without fixing. So without fixing, one source and one element are thermal GA from T junction to T ambient. So the equation will be Tj is equal to Pd R thermal Ja plus Ta. Okay. So your TJ should be 20% less than T max. So look at your TJ. Now, how much your TJ of this part? So just now for on semi, we have maximum junction temperature capability up to 150 degrees C. Now for TJ, your maximum junction temperature also can go up to 150 degrees C. Okay. So your maximum TJ will be 0.8 times 150. So you get 120 degrees C. So this is your maximum TJ that you will run for your set your device. Right. So TA assume at 40 degrees C. What else? VDD is 400 volts. I MS 20 ampere. Okay. PD is equal to I square RDS on at 120 degrees C. So your RDS on at 120 degrees C is how much? If you look at your data sheet, RDS on at 25 degrees C is 0.008 volt. Sorry, ohm. But at 120 degrees C, how much is your RDS on? RDS on, RDS on. RDS, drain to source resistance normalized versus temperature. Okay, we have here 120, 140, so 130 here, 120 around here. So 2.0, so your RDS on normalized. See, 120, almost 120. We put that 120. So 0. You can take here 0.08 or 1.02 centimeter. Let's say you want to fix it at typical. So later, if anything happens, so you have to, if this total reject, so reject. If accept, accept. If this one, still can consider further. Okay, let's say we take this one 0.088 times 0 times 2.0. So 0.088 times 2.0. So you dapat apa ni? 0.176. 0.176. Oh. So you can dapat your PD equal to 20 squared times 0.176 becomes 70.4. 70.4 watt. So this is your dissipated power when you run full current of 20 ampere throughout your device. 70.4 watts. Right. So you must balik dalam TJ at this moment. How much? 70.4 times R thermal JA. You look at your device, how much the R thermal JA. Thermal resistance Parameter JC 3.6, JA is 65. 65 plus 40. So it becomes how much? Your TJ. 4616. 4616 degrees C. So it burns much faster compared to on semi just now. If you remember on semi 3304 04. Now with Vishay is 4616 and your Vishay is 4616. It burn much faster. So that's the consequences when you run without heatsink at full current. So now we same step, take a look at the system or the device, how much we can cater without heatsink. So we shade without heatsink, full current. So this is what it was. Then without heatsink, how much actually the current we can cater. Now we share without heatsink. I max sama dengan berapa? So same, TJ equal to PD thermal JA plus T ambient. So we shall set at our TJ 120 degree C. So PD is our PD max that we have to calculate. Thermal JA we already know now. T 5 T ambient 40. So this is our PD max to maintain our junction temperature. So how much is worth? 120 minus 40 divided by 60. Hold on. 120 to minus 40 divided by 65. We're going to put 1.23 watts of maximum dissipated power that we should conduct throughout the switch to maintain TJ at 120 degrees C. So PD max is adalah I square RMS max time RBS on at 120 degrees C. So 1.23 equal to I square RMS maximum time RDS on, which we have calculated just now, 0.176 ohm. Ya nak, sorry guys, bateri habis pula ya. So IRMS 1.23 divide by 0.176. .988 so 2.64 ampere. So if you compare with your on semi, without heatsink, maximum current is 3 ampere. For V-shave, without heatsink, maximum current is only 2.6 ampere. So this is the performance comparison between the two devices. What up? It's not 3, now only 2. So this is the same thing that you should do inside your lab. Right? Without heatsink, how much the performance or the limit. With heatsink, how much the heatsink you need to touch your device. Okay. Alright. Yeah, this is without heatsink. Then, what if we want to put a heatsink? So on semi, with heatsink, how much the heatsink you need to calculate? So same goes to your V-shape with heatsink. With heatsink, how much the size of your heatsink you have to buy or you have to select for your device. So V-shape with heatsink. So TJ will be, it has now 3 elements, which is our thermal, JC, our thermal, TS, our thermal, SE. You conduct from your junction down to ambient through your case and through your heatsink. Your PD, our thermal JC, our thermal CS, our thermal SE. Yes. So your TG is 120 degrees C. Usually, our thermal JC will be provided. This is the heatsink or your thermal paste. Thermal paste here will be provided. This is the part that you have to find out. Heatsink. Okay, junction we set at 110 degrees C. So PD is the amount that we have to calculate when we conduct IRMS of maximum, which is 20 amperes now. So JC dapat daripada datasheet. So datasheet, this is the unknown that you have to calculate. This one already being provided. The ambient 40 degrees C. So how much is JC? So JC 3.6 is. So 3.6 CS 0.5. SA is our unknown. Ambient is 40. Sorry guys, battery almost out. Okay, PD we have calculated just now. You see, the PD when we conduct at 100% of current. So this is our PD, 20 ampere square times R thermal between drain to source at 120 VC of 0.176 ohm, dapat 70.4 watts. So 70. So PD is 70.4 watts. So kita akan dapat 120 sama dengan 70.4 times 3.6 plus 0.5 plus R thermal SA plus 40. You rearrange all the formula or the calculation because in between we have marks as well. So you akan dapat R thermal SA of how much? So don't skip the calculation step. Please follow. I have to skip because my stack battery ni almost out. Dah out dah pun. Critical situation ni. So calculate for the values. You can dapat 120 minus 40. Then divide by 70.4 minus 36 minus 0.5. So it becomes negative. Oh, jadi dahsyat. Negative 35.36 AC per watt. Apa maknanya ni? Okay, guys, okay. Anybody can confirm my calculation?
Sir,
Ya.
yang R thermal JC tu 36 ke 3.6?
3.6.
Okay, thank you sir.
3.6 kan? Yeah. 3.6. See? 3.6. 120 minus 40 divided by 70.4 minus 3.6, okay? Minus 0.5. Kecil sikit lah. Negative 2.96. Yeah. Anybody? Still negative 2. So this is the value of required heatsink for this part when you want to run at full current of 20 ampere. Yes, now for on semi, heatsink is 0.03. 0.03 degrees C per watt. So on semi. So VC we need negative 2.6 degrees C. Anybody can confirm the value first? Dapat sama ke? Then only we conclude on the findings. Because the aim is not just to get the value. We want to know what the value means. Apa maksud value tersebut? Okay. Can anybody confirm? Get this value? Tak lagi sir.
Dapat saya.
Sama lah, dapat sama.
Sama sir.
Okay, okay, baik. Okay, means that if let's say this is the correct value that we have calculated, it means that even though at the front page of our data sheet, it says it can conduct up to 29 ampere. And for our case, we just need to conduct or to use the part to flow in or to process only 20 ampere RMS. But when you calculate, we shall see that it needs heatsink. Without heatsink, we cannot operate. Or without heatsink, it can cater up to 2.64 ampere only. So with heatsink, the heatsink size need to be attached with negative 2.96 degrees C per watt. The lowest best heatsink is 0 lah. So negative means that we have to force cool. Letak ais kah, letak fan kah, radiator kah, which is not feasible lah. Not feasible. So it means that we have to select other parts. Select other parts. Sekarang ni bukan nak pilih heatsink lah. Memang heatsink ni tak possible lah. We have to select other parts or we have to reduce our current rating. We cannot use 20 ampere. So without heatsink, we have to reduce down to 2.64 ampere. If with heatsink, so we have to take a look how big our heatsink we have in place or in our storage. Let's say we have certain values of heatsink, so that heatsink to be applied. So what the amount of current that we have to produce. Sama macam apa yang kita buat dekat this part now. Okay now. Without heatsink, we can go up to 4616 degrees C of junction temperature. So we try to see if we have put no heatsink, how maximum the current can go. So it can go up to 2.64 ampere. Same goes to this process. With heatsink, if you want to ramp up to 20 ampere of current, so how big heatsink we have to provide? It shows that we have to provide the negative value of heatsink or force cooling. So it's not feasible. So next step is that if we have certain value of heatsink, let's say we have a 3 or 5 or 10 degrees C per watt of heatsink, we put it back inside our calculation. So we can try to scan how much the value of current that can safely be processed or conducted by the device for that certain size of heatsink. Nampak tak? So that's the process lah. Dia akan pergi ke depan, patah balik belakang, pergi ke depan balik untuk cross check. Faham tak maksud saya? Sepatutnya dia punya next process, because the time is almost due. The next process is that we shall pick one of the heatsink around here. Let's say we search for heatsink. We will search for heatsink, come out with multiple of heatsink. See, natural convection heatsink. We have fan cooled heatsink, so this is the type that is. Sorry guys, terputus pula semula. Okay, ulang sambung pula. So when we take a look at heatsink, contohnya bila kita type in heatsink natural convection. Nampak tak? Heatsink natural convection. Dia akan keluar about 1000 something of selection. So the most important parameters to be considered upfront is our thermal resistance. So let's say we need set certain value, so we take the next lower value. Let's say we need 4 divisi per watt, and 4 divisi per watt that we required, but we just select the lower one, okay, 3.89 and 3.9 at least. So show the result. So select the most appropriate pattern or layout that's suitable with our design. And also you can select and compare in terms of their price. You see, sometimes the part costs cheaper than heatsink. The part around 10 ringgit. When you come to heatsink, you can see here double or sometimes multiple of the device price itself. So that's why I told you we have to consider in terms of the whole system, the part together with the heatsink, how much the price compare with the two different manufacturer, and the total price with heatsink, and which one is more feasible and economic and with our application. So you take the value and the degree C per watt here, and then you compare back with your calculation. So how much actually it can cater the maximum current of your device of your system. So compare in terms of the whole price with the same level of current. So you select one. Okay, that's all for our discussion today. And this is maybe the more related to your test to come. And I will focus on the conduction losses first, because you by right you have to consider up to conduction plus switching losses, and but to make it less stress and with our certain issues. So we shall focus on the conduction losses first. Okay, any question so far? Any question? So for attendance, I will not take yet, because most of you all, I don't think you can come to class because Senin duty, Thursday pun duty, so not. Okay, tak. Tak berbaloi lah attendance. Okay.